going to show you a clip. This is a video clip from 2008. So BBC One actually traveled to Utah and shot a 1-hour documentary. I think it's called Hot Planet, and it is online. You can actually watch the entire thing. This is just one clip from it. And I was brought on as an advisor for the documentary, so it was quite an honor. But I wanted to show you this clip because it includes, after 3 minutes or so, I'll stop the clip, but it includes some pretty dire predictions. So, but also a nice summary explanation of carbon capture and storage.
In 2010, the US government will begin an $88 million test project to investigate how it might safely store the captured CO2. To find out what they're planning, I need to take a step off this cliff. These massive, awe-inspiring formations are sandstone carved by wind and water. And it's this rock that might provide us with a storage solution. Because sandstone is so porous, you could inject carbon dioxide into it, filling up the spaces. The 300-meter canyon wall I'm descending is made up of different layers of sandstone. My destination is much further down. This rock is called the Wingate layer, and it's into this kind of sandstone that they're planning to inject the carbon dioxide. The layer just above is much denser, so the idea is the carbon dioxide gets trapped here. Nobody's planning to do this in a canyon. Instead, they'll do it at least 1 kilometre underground. If the natural rock seals hold the CO2 and keep it held, the potential for geological storage is vast. Sandstone could store 50 years of Utah's emissions, a state of 2.5 million people. There are different kinds of geological storage sites that could also work, but the CO2 still has to get there. Carbon dioxide is expensive to transport, but since coal and gas are often found in or near rocks like these, many power stations are already built right on top of places you could store the CO2. In 2010, 1 million tonnes of CO2, the equivalent annual emissions of a small power station, will be injected into Utah sandstone.
Carbon capture and storage could allow us to carry on using fossil fuels like coal while we develop cleaner, emission-free technologies. But at the current rate of development, widespread use is still at least 10 years away, and that may be too late.
If we want to limit temperature increase to around 2 degrees Celsius, then we have only 7 years more in which we may allow emissions to increase. But beyond 2015, they'll have to start declining.
What does a 2-degree world look like?
It doesn't look very good. I mean, with 2 degrees, we certainly will get very high sea levels over a period of time. Sea level by thermal expansion alone will be anywhere from 0.4 to 1.4 meters.
And it's not just the
Just literally 2.5 weeks ago, interviewing the former chair of the Intergovernmental Panel on Climate Change passed away. So we wanted to acknowledge that from the interview. And he stated that if emissions continue to increase, that 2015 would be the tipping point. Sea level would rise by as much as 1 meter. And the data the data are interesting. And I wanted to show this EIA, Energy Information Administration, series of plots because this was assembled in 2007. So again, about the time that these interviews were assembled and put together for the documentary in 2008. EIA was also putting together its portfolio of forecasts. So this is the base case. So 1990 emissions about 1.75 million metric tons in the U.S. So this is United States only, not worldwide, United States only. And for that 2007 forecast, just efficiency, and I also love to show this because it talks about what happens by 2020, so we're there now. So it's kind of interesting to go back and look post-mortem at these things. Efficiency increases by at least 1.1% per year. That has not happened. It has actually happened in natural gas-fired power plants. So new power plants that came online have increased their efficiency. But renewables, 30 gigawatts by 2030, with a target of 70 gigawatts. So that means 70 gigawatts. So a typical large power plant is 1 gigawatt. So and, you have 3 units or 2 units at 500 megawatts. So one large power plant, 1 gigawatt. So 30 power plants worth of renewables, which it's not. Certainly, we've achieved a lot in terms of wind power, but maybe not 70 megawatts. Nuclear generation, we certainly don't have 12.5 new nuclear power plants in the U.S. So, and not even one new one. I think there's still some in the permitting process that we have on that. Advanced coal generation, 40% new plant efficiency. There was a project called FutureGen, which was to be an emissions-free coal-fired power plant based in Illinois. President Obama's, former President Obama's home state, and he was the one who actually shelved that project in 2000. Casey, do you remember when they shut it?
So I came here in 2013, that project was going on, but nothing soon after that.
Okay, and so about 2014 is when FutureGen was, which that was to be the basis, FutureGen was to be the basis of its coal generation testing. And then CCS, so widely deployed after 2020. So that's kind of, and it's certainly deployed. There's certainly a great deal of CCS deployed now, but only in oil fields. The only country on the planet that has deep saline storage just for sake of deep saline storage is Norway, and Norway has a carbon tax. It's the only major economy that does have a carbon tax. So market-driven versus tax-driven, it's at least connecting those dots, it seems pretty clear what will motivate CCS just for the sake of CCS. Not to disrespect enhanced oil recovery, but that is probably, well, it is in the U.S. the only operational CCS ongoing. So the goal, though, is to continue using fossil fuels. They're not going away. They're just not. We will continue to use coal, more natural gas than coal. And in fact, emissions have changed quite a bit. And I'll tell you what. So thinking back to those 2007 forecasts and the interview that was shown. So in 2007, right in this time frame, the U.S. carbon dioxide emissions had just jumped. And in 2007, this is that increase. 2008, sharp decrease. 2009, an even steeper decrease. Any guesses as to why there was such a drastic reduction in CO2 emissions? Pardon me?
Fracking.
Yes. So in a nutshell, the word is fracking. So hydraulic fracturing of tight gas shales and some oil shales, of course, but mainly gas shales that effectively flooded the market with natural gas, reducing the prices of natural gas, and motivated fuel switching and much more extensive gas usage, much less reliance on coal. So the emissions from coal generation were reduced because those plants that could utilize natural gas that pressure, that downward pressure has increased. So this is the current plot. I just got these data literally the night before last from the EIA website. There's a steep reduction in 2009. And then there was a change in gas prices, which caused, again, another jump, and then reductions, jump, reductions, and then there's been a slight increase again in 2018, but nevertheless, the trend is changing. And then the forecast, short-term forecast, and this was from 2019, was a reduction in 2020 and 2021, this year, next year. And an even longer-term forecast suggests that emissions are going to go down even further. So is it good news? Well, I think it's encouraging because it does provide more time. It certainly doesn't eliminate the CO2 emissions, which is the ultimate goal, but as the former chair of the IPCC suggested, we need time to bridge technologies to make our way to renewables. The big obstacle with that is baseload. So solar and wind power can't provide the baseload that's needed. Nuclear power does provide baseload. But there's, since 3 Mile Island and other nuclear power plant accidents occurred, that's not been on the radar screen, so to speak. So, benefits of geologic sequestration. So this is where I'll get into some of the science. So reduced atmospheric CO2 concentration, ostensibly that will delay, at least reduce the rate of increase of warming. Now, even though U.S. emissions have decreased, emissions from China, India, and other developing countries have still increased. So we're not completely out of the woods. The emissions forecast for the U.S. might look pretty good, but other countries are not or cannot follow suit. So we're still facing that issue. And we don't yet have an experiment to prove it. But reduced CO2 concentration, certainly even if CO2 is not responsible for global warming through the greenhouse gas effect, I think ocean acidification is certainly a great motivator for reducing CO2 emissions. At least it really is for me. And then also just the act of mandating, either instituting a carbon tax or otherwise, if it motivates switching to cleaner fuels. And here's a nice example from oil and fuel bunkering in the shipping industry. There's certainly other tangible, if only secondary benefits. So it's a good thing. And then lastly, also promoting energy independence. So fracking, if this was just mentioned earlier, if it's unregulated, fracking is really can have some really negative impacts. But if it's regulated properly, it has actually dramatically reduced the U.S. carbon emissions in any case. So, and then most of our work in 2007, 2008, when that documentary was shot, so the $88 million project that was discussed by Kathy Sykes was for Utah sandstone. That was for a deep saline test that we proposed. And actually, I wrote the proposal for that test in Milagro coffee. So in those afternoons when I was here, I wrote most of that proposed work for injection into Utah sandstones. But in 2010, President Obama appointed, actually he appointed before 2010, but President Obama's undersecretary responsible for fossil energy, Chuck McConnell, mandated that all CO2 projects, mandate is a strong word, strongly encouraged, put it that way, switching to enhanced oil recovery projects from deep saline projects. It wasn't required, but it was strongly encouraged, which I interpreted as a requirement. So we changed to oil recovery, and we moved the project to northern Texas. So I'll talk about those results, and that's part of the, as Reed mentioned, the Southwest Regional Partnership. Again, started in Socorro 2002, and actually began in 2003, and late 2003, and it will end in 2023. So the project will, all of these projects are CO2 EOR, including this one in northern Texas, which is our Southwest Partnership project. And the Southwest Partnership consists of, it's still based out of New Mexico Tech, so I wrote the proposal when I was at New Mexico Tech, but then when I moved to University of Utah, we left the project at New Mexico Tech in terms of management, because changing 30 subcontracts is a big, tall order, so we left the structure intact. So I'm still directing the project, but from the University of Utah instead, and work very closely with folks at New Mexico Tech still. And it also includes the geological surveys and major universities in the Four Corner States, plus Wyoming, Kansas, Oklahoma, and Texas. So, as well as the nomination. So a pretty big consortium. It's been daunting. Reed asked me what my day looks like typically, and it's a lot of phone calls. New Mexico State is a part of that through Joel Brown. He's with USDA and also an affiliated point with New Mexico State. And Joel couldn't be here tonight. He's in Nebraska. In his words, he's testing out his resilience to coronavirus. So New Mexico State is part of the consortium in that regard. And this is another picture of the, show this graphic, a different version of this graphic early on, again with the power plants, the pipelines, and then all of these black dots are oil wells. And so all those black dots that lie close to pipelines are CO2 enhanced oil recovery projects. So there's actually a ton, or many tons of CO2 stored by enhanced oil recovery. And let's see.
So the CO2 stays down the hole when you inject it and get the oil out.
Yeah, so the question is, CO2 doesn't stay down the hole when it's injected. It is reproduced. A lot of it stays behind directly, immediately. Some of it, though, is reproduced with the oil, because the concept is that CO2 dissolves in oil and reduces its viscosity and its density, making it easier to produce the oil. So it is reproduced, but then oil companies don't like to pay for more CO2, so they separate the CO2 from the oil and re-inject it as fresh CO2. So ultimately, all CO2 in these EOR, enhanced oil recovery projects, is stored effectively. And as one study, and I've got copies of any papers that I talk about, I've got a paper that in which it details a study that was conducted discussing quantifying whether enhanced oil recovery with CO2 is a net storage positive. In other words, you ultimately store more CO2 with CO2 enhanced oil recovery than if you don't inject CO2. And the answer is that if you factor in the oil that's combusted, turned to natural gas combusted, that creates a lot more CO2, right? So, but if you consider that the oil will be produced no matter what happens, it's better to inject the CO2. Kind of a sour grapes kind of rationalization, but it's still true. It still applies. But it does, to answer your question, it does stay down. If only because the companies are motivated provide more CO2, so it definitely stays on. A great deal of it, though, upwards of 30 to 40% can be quote unquote lost and never dissolves in the oil, it just stays down. We actually partnered with a fertilizer plant and an ethanol plant up in Kansas. Actually, we didn't. The operator who we partnered with, which was Chaparral Energy out of Oklahoma City, now taken over by another company since then. But they were responsible for these local CO2 pipelines. They invested upwards of $90 million building these pipelines, but rest assured they've made their money back. So, but this is the farms of Texas. This is the Oklahoma Panhandle, the Texas Panhandle, and so a lot of the results I'll show you pertain to that site. Let's see. And so these are a series of what are called 5-spot patterns. That means you've 5-spot, meaning that you've got a well surrounded by 4 surrounding wells, okay, in a square. So there's 5 wells. Typically, the one in the center of the square is a producer, and the 4 on the outside are injectors, and start out injecting water to increase the pressure to drive oil out, but then when that becomes ineffective, then CO2 is injected to dissolve the oil. And these are the well patterns that were drilled and instigated and injected CO2 starting in 2010, and then 2013, 2016, and then plans are now for 3 potential new patterns in 2020. So they are I'll bet it doesn't happen though, because much like everyone in this room, oil companies are waiting to see the outcome of the election, because energy policy is dictated pretty strongly by the office of the presidency. So with that, 93% of the purchased CO2 still in the system. This gets back to your question from earlier, does all the CO2 stay in the ground? And I said yes. Well, that which is injected, if they flare it, so roughly in this area, 7% of the CO2 is flared, because they have to market prices if it's less expensive to sell the oil than it is to not produce it. The CO2 is still flowing, and so they will actually flare it. They'll also flare excess natural
How
gas.
would you flare CO2?
Because they flare it with natural gas. So they don't just release the CO2, they will flare it with natural gas from the site, which these sites are not actually, that field produces oil, but it also has an excess of natural gas, which they don't pipe out. So there is some that, everything that goes into the ground stays in the ground. And as you can see, thousands of barrels of oil. I don't know what the current price of oil is, but it's at least $50 to $75 per barrel. So you can see that they've certainly made their investment back. But on the flip side of that, we've had well over 1 million tons of CO2 net stored in the system. This number is 1.2, I think, actually now. This is July 2018. We're actually up to 1.4 million. So it's clearly that is CO2 that would not be stored in the system otherwise. It would just be emitted from the fertilizer plant and the ethanol plant. So there actually, in this case, is a net reduction of CO2 emissions. So, yay. But at the same time, it would have been nice if this had been a deep sailing project and not an oil production project, which is what the original plan was until 2010. Now, some cool science came out of this. So I do want to bring up the science that some of the science that we've carried out. As Reed mentioned, in addition to the students at the University of Utah and at New Mexico Tech and actually, New Mexico State, Joel Brown has published multiple papers out of this project, and all of the other states. The project itself would earn tenure at any university. It's published so many papers, and it's been really prolific science. And I'm just going to talk about just a little bit of it, some of the cool stuff. We injected, over the past 6 years, we've injected both aqueous phase tracers as well as vapor phase tracers. So tagged CO2 itself with tracers, and then also tagged water with tracers. And naphthalene sulfonate is the aqueous tracer that the only one we use. We tried many different PFCs, fluorocarbons, in the parts per billion range, but that's sufficient. But the results for the vapor phase were pretty not helpful, let me put it that way. But in terms of the aqueous phase tracers, we saw, so this, there were at least 6 different wells. In fact, let me go back to this graphic. It's 2, 3, 4, 5. There's a 6th well that's not shown on here. I don't know where the symbol went, but there were 6 wells in which we injected both aqueous and vapor phase tracers. And just the results for this one, well 13-3. You can look at the breakthrough times on this, and I'll blow up this graphic in just a second, but the results are pretty startling. And initially we thought, okay, the closer production wells would produce more tracer. We'd see what's called breakthroughs. So tracer is a unique chemical tag. So in this case, a PFC of naphthalene sulfonate, which is not present in water, but it's not toxic. It's injected in parts per million or parts per billion, so it's a really small amount. So it's environmentally, it's not threatening to the environment in any way, but it's unique. You can detect it even at parts per billion levels. So we injected that to see when the CO2, because you inject CO2 and CO2 comes out the other side. You don't know when that individual molecule of CO2 actually made it from one well to the next. So we tagged it with tracers to see what is the speed of CO2 and other oil and water and brine moving through the system. And we expected good results, but not this good. I mean, these were really just fabulous results. Effectively, you have these wells up here, which these squares are 1 mile on the side. So almost a mile away, 11 days breakthrough. Whereas right next to it, less than a half mile away, maybe a quarter mile away, 257 days. So that means that the rock between here and here is much denser, much less permeable, and there's some kind of rocket pathway going north to these other 2 wells. There's rapid breakthrough. So what we identified, what was visible in the seismic images were some suggestion of faults, but again, nothing to prove that those were faults. There were big cracks in the rock straight up. But this basically corroborated that, strengthened that interpretation. So if you look at these, just blowing up a little bit, most of the tracer recovered actually was right here. So the light blue is the relative amount of tracer recovered. The dark blue is the arrival time of days. So again, basically we inferred, and seismic, if you've ever seen seismic data, it's really difficult to interpret. You'll see a seismologist kind of get sideways against the paper and try to interpret it. I mean, it can be really difficult to interpret seismic images. And we thought, our seismologists and geologists thought that these were faults. But then when we saw the tracer results, and effectively these dotted lines are the interpreted faults, inferred faults. Basically means that the tracer results suggest that the faults are high permeability conduit for flow, parallel to the fault, within the fault, but then a barrier to flow across the fault. So that's why we've got basically 257 days coming across here. 39 days going across this way, but because of the proximity, how close it is, most of the trails are actually busting out right there, which makes sense. And then with respect to the gas phase tracer, so we got the aqueous phase dissolved in the water, the brine, nice and well behaved, just as we thought it would be. And on the right side, the pointer's not wait for it to recharge. On the right side is showing the vapor phase, and you can see that in the middle plot right here. So after injection, it just kind of recovery and detection goes kind of haywire. So we've effectively abandoned the PFCs, the aqueous phase tracers, and we're sticking with the water phase element. We haven't abandoned it. We just we use it for gross interpretation, but not detailed. So, I thought I blocked up. So nice, well behaved on the aqueous side, not so well behaved on the other side. But really interesting data, and tracer people who work on tracers for their career just love this data. So, all right. So what we've done with this is the first step in the process, using geophysics, seismology, structural geology to interpret what we think the geologic setting might be, including faults and fractures and otherwise. And then use the tracers to interpret the hydrologic signal induced by those features and whether or not the features really exist, and then use computer models to simulate and further interpret results. And it's actually it's number 2, the tracers, and then number 3, the actual geophysical model. So this is a rendering of non-aqueous liquid saturations. That basically means CO2 and/or oil. We've got it mapped out for different results. This is actually the CO2 because you're seeing these blue. No, this is oil because that's what's being produced. The blue is the low saturation, the red is the high. So, okay. So that's some of the science really. That's that ancillary science that is probably, I think, one of the biggest benefits in the short term. The risks. High costs and impacts on the economy. So especially if the carbon tax were to be instituted, impact on drinking water, potential for arsenic release, other heavy metals, induced seismicity, and as mentioned to Reed earlier today, the first time that a major earthquake happens due to fluid injection, CO2 injection, will be the last time. This is probably when someone solicits my advice about what do we need to pay attention to, it's the seismicity, because the moment that happens, it won't happen again. I mean, it's something that won't be tolerated by policymakers or the public. So, surface leakage of carbon dioxide. The maximum rate of surface leakage will be the maximum rate of flow to the leakage point on the subsurface, which this stuff moves pretty slow. We're talking centimeters to maybe a meter per year. I mean, it's you can get the breakthrough in 11 days of a tracer, so that fluid does move pretty fast. But in terms of that CO2 breaking out, I guess Reed looked up the numbers for Lisa Canyon, a natural gas leak in Southern California, and we calculated, I think it was 500,000 tons per year is the effective rate. Okay, and that's a catastrophic leak of methane. If you have the equivalent leak, compare that to a power plant which produces about 50 million tons of CO2 per year. Okay, if you're leaking 500,000 tons of carbon dioxide, well, it's a very small power plant equivalent. So it's the bigger issue, I think, is the induced seismicity and the potential for drinking water impacts. Okay. some drinking water results. So we've conducted some column experiments, took some samples of the actual rock and sands in the field and above the field where drinking water is actually drawn out. And then we injected those sands with carbon dioxide along with the brine that's present in the formation. And then we examined pH, that's acidity, as well as calcium, which is a benign ion, and arsenic. We also looked at uranium and otherwise, and manganese. But in all cases, as soon as CO2 injection ceased, so did the movement of those constituents. And arsenic in particular, I want to show that specifically. Arsenic is a really small release as long as it's moderate leakage. So if the leakage of CO2 to that aquifer is detected early enough, I mean, if you've got massive leakage of CO2, then that's obviously going to release a lot more. But if it's moderate detected and it's detected early on, and you also have to have high concentration of arsenic to begin with. So lesson there, don't inject the air formation that has a lot of arsenic in it. But, so these do need to be careful and deliberate. Trace metal increases, we've got pH, this is manganese, calcium, uranium. Actually, there's pretty minor amounts, trace amounts of uranium, but in all cases, as soon as CO2 injection ceases, both the experimental results as well as the simulations suggest that the drop-off of release of those will be pretty significant. And really wanted to show these guys because uranium is of interest, it's uranium, but again, it's very few places around the country that have high enough concentrations of uranium to be a major factor. Manganese is more of what the EPA calls a nuisance chemical. Secondary drinking water standards for nuisance chemicals. Manganese will impart a rust color to your laundry, for example, and make your water taste bitter, but you'd have to ingest a lot of manganese for it to be really, cause major problems. Arsenic, on the other hand, is a carcinogen, and so it's pretty significant. This chemical formula, I just wanted to alert you that S is the mineral site in a clay, for example, so it's not sulfur. It's a mineral site, so the oxidation of acidification can release arsenic, but arsenic and hydrogen ions compete in the same sites. And as soon as calcite solution, which is usually present, and it doesn't even necessarily need to be calcite, it needs to be anything that increases the pH back again. Once pH is increased again, then the arsenic is reabsorbed. So it's, I guess the lesson here is that choose sites that don't include high concentrations of bad stuff, and secondly, be very deliberate and careful with the mitigation plan and how that will be addressed after the fact. So, all right, induced seismicity. So I'm going to wrap up with this quickly. So I'd like to get into some question and answer. It's already 10 after 8. So injection in the Aneth field in 2007. So this is Aneth is southern Utah. This is now Dr. Ninglu. He was a PhD student at New Mexico Tech at the time. And this is one of the injection sites. And Ning helped oversee some CO2 pipeline that was laid. And we injected, to date, it's a bit over 550,000 tons. We're still monitoring. And this is in the Desert Creek Formation. I'm gonna, if any of you are interested in the geology, I could talk to you for several hours about it, but we'll move on from it. This is a map of the field showing the top of the Gothic Shale. So this is the capping unit of the injection oil reservoir. So this is an oil recovery project again, and this is the injection well. And And so you can see it's kind of an elongated structure. And this is actually Navajo Nation Oil and Gas Company employees who are duct taping, literally, seismometers, if you will, sondes, to the drill string to install an oil. Put a 16-level array to monitor passive seismic activity, which we had planned on monitoring seismic energy coming from Colorado, but it turns out that the field itself was swamped. And in fact, we saw these are cumulative number of events, so you can see dozens of events over the period of a year, thousands of seismic events induced by the injection. Thousands of events. Okay, but the key with this is that all of the events are -1 magnitude or less, so they couldn't be detected at the surface. You had to have a high-resolution seismometer detector to sense these things. Okay. And when we mapped out the hypocenter, so epicenter is the mapping of the seismic event at the surface. Hypocenter is the volume, so the three-dimensional location. And we were able to resolve 2 previously unmapped. And these weren't even suggested by seismic lines, like I showed in Texas. These were just unknown, but they have to be mapped faults that were slipping as a part of the pressure change. And additionally, we tried to correlate CO2 injection in the field to the seismic events. That didn't work. I mean, it's apples and oranges, but if you map it out compared to, let's skip ahead here, to water injection. So we didn't see much of a correlation here, but with water injection, we actually saw saltwater disposal and microseismicity. That trend is not meaningful, but if you look at the number of events per week and then map out the volumes of water injected, you start to see a correlation. And then the distance between SWD on this graphic up here and the red dot hypocenters. The distance, if you calculate the time required for pressure to migrate from this SWD site to these faults, is about 50 days. So if you actually, you can see some correlation, but if you subtract or add 50 days, the correlation is much better. So we have a really good, consistent picture of what's called the hydraulic diffusivity, or the permeability of the rock formations, and how fast pressure should migrate, and the actual seismic events on these faults, which is pretty gratifying. This is a fabulous example of induced seismicity, especially since the induced seismic events are really micro seismic events and don't have a negative impact. So, what I have in my hip pocket at the end, if anyone's interested, is there's a natural earthquake that occurred about 15 miles from the field, magnitude 3.6. And after that natural earthquake occurred, oil production almost doubled. So it literally shook the field up and increased the permeability of the field. So higher magnitude earthquakes are a big deal. So, all right, what's best for geologic sequestration? Well, I think carbon capture and storage in deep saline formations underneath oil fields, because if you think about it, we've got a huge amount of saline capacity, not so much capacity in oil reservoirs. So really the oil and gas reservoirs are the low-hanging fruit, but the capacity comparison is, oil and gas reservoirs are negligible compared to the volume that's available in deep saline formations. So why not go to those deep saline formations underneath oil and gas reservoirs, because then effectively the oil reservoir becomes a catcher's mitt. If the CO2 leaks from that deep saline formation, it migrates upward, it's buoyant, it's less dense than water. So water is 1 gram per cc density. CO2 is about 0.75 grams per cc, so it will buoyantly rise and then hit the oil filter. So it's a great approach. In fact, I think I did multitask that. So when oil prices are high and don't favor production, store in the deep saline formation, but when oil prices, actually, that should be reversed. When oil prices are low and don't favor production, store in the deep saline formation. When oil prices are high and you want to produce oil, then use that CO2 to produce oil. Okay. I'm going to wrap up with the conclusions and leave about 15-20 minutes for questions and discussion. And I hope you'll ask some tough ones. Thanks so much.